Hello dear students, I hope you are enjoying this lecture series on modern physics. In our last lecture we derived Maxwell's equations. Today we will get a bit deeper. We'll talk about the symmetries of Maxwell's equations and then we will try to derive the electromagnetic wave equation. And there some interesting physics lies once we derive that equation. So let's get started and let us see what we did last time and get going with today's lecture. So remember that we started with the Gauss law of electrostatics and then we put it in the differential form to get the Maxwell's first equation, which was that divergence of electric field is rho by epsilon naught, where rho is the electric charge distribution or charge density. Then we know that the second equation was nothing but the differential form of Faraday's law, which tells us the curl of the electric field created by a changing magnetic field is given by the rate at which the magnetic field changes, the curl of electric field. And this electric field is created not by a static charge, but a changing magnetic field. So these were the first two equations. This one was the differential form of the Gauss law. It tells us the divergence of the electric field is charge density divided by epsilon naught, where epsilon naught is the permittivity of free space. And the second equation tells us it's actually the differential form of Faraday's law. It tells us that electric field created by a changing magnetic field, if that electric field circulates around that changing magnetic field, or the electric field has a finite curl, it forms closed loops. So remember, an electrostatic electric field never forms a closed loops. These are open field lines, whereas the electric field created by a changing magnetic field forms closed loops. There are two origins of the electric field. And if the magnetic field is not time dependent, then we have two electrostatic equations. One is that divergence of E is rho by epsilon naught. Other would be that curl of E would be zero if magnetic field is independent of time. These were the two equations that Maxwell's first two equations, that they're related with the electric field, how electric field varies from point to point in space. Now we will write the other two equations. And the third equation is nothing but the fact that magnetic monopoles do not exist. Since magnetic monopoles do not exist, and they are always in closed loops, then if you have any closed surface in a magnetic field, net flux through that flux through that surface would always be zero. So the fact that magnetic monopoles do not exist experimentally, that boils down to this differential equation, that is divergence of the magnetic field is zero. This tells us simply that magnetic monopoles do not exist, or Gauss law of magnetism is said that total magnetic flux through a closed surface is always zero. Then we have the Ampere's law, and it needs to be corrected if you need to incorporate this local conservation of charge. And we did that in our last lecture, and we corrected the Ampere's law and got the Maxwell's fourth equation. And this equation tells me that the curl of the magnetic field is mu naught current density plus mu naught epsilon naught, the rate at which the electric field varies with time. Right. So magnetic field has two origins. One, it can be created by a current density, current passing through a wire can create a magnetic field which will loop around that current carrying element. And then we have that magnetic field can also be generated by a time varying electric field. So if the electric field varies in time, it generates a magnetic field. And again, that magnetic field, even if it is generated by a time varying electric field, it also is in closed loops. So the fact that whether you have a steady state condition where you have constant current flowing through a wire and you have what's called as magnetostatic right condition, that will have a curl. And even if you don't have a steady state condition where electric field is dynamically varying with time, you will have a magnetic field that will also be curving around, that will also have curl. And in both the cases, doesn't matter what the origin of magnetic field is, the magnetic flux is going to be zero. That means if a electric field creates a magnetic field, that would be in closed circular loops, and so would be the magnetic field created by a current density created by a current carrying conductor. So these are the four equations, and we call them as Maxwell's equations because they unify electricity and magnetism principles. They completely mix the electricity and magnetism phenomena. So you can see that now the electricity and magnetism are related to each other. They are dependent on each other. A changing magnetic field creates an electric field. A changing electric field creates a magnetic field. Creates a magnetic field with some curl. So this is that electromagnetism, all rules of electromagnetism have now been presented in the form of these beautiful differential equations. Now these equations, they look beautiful, but there are certain problems with them. So we'll see that what kind of challenges are there in solving these differential equations. The first thing I will try to see that what are the symmetries in these equations, and some simple symmetries. We'll not talk of some higher order symmetries like gauge symmetry, Laurent symmetry, because right now you have no understanding of relativity, and we'll talk of very simple symmetries. Let's talk of time reversal symmetry. So let us see whether these equations are symmetric under time reversal. We'll talk about time reversal symmetry. What time reversal means is that you flip the direction of time. So when you flip the direction of time, what is going to happen? So which are these equations, do these equations retain the form even if we flip the direction of time? You see, when you flip the direction of time, the electric field does not flip its direction, right? So because the direction of electric field depends on the nature of charge, it does not depend on whether time is going in forward or reverse direction. So keep this in mind that the electric field will not change sign under the reversal of time, but the magnetic field will change its sign under time reversal. Right, magnetic field will change its sign under time reversal. And since current is going in a wire is actually dictated by the motion of charge, right? The charge is moving in some direction, which means that it is in the direction of the velocity of the charged particles, right? Current density. Now, if you flip the direction of the time, the direction of the current density will be in the opposite direction. That will change, right? And the magnetic field will change direction under time reversal. So if t goes to minus t, if t goes to minus t, this is called time reversal operation, then E will still go to E, means E will not change sign, but B will change sign, it will go to minus B, and J will change sign, that will go to minus J. Let us see whether these equations are they accept time reversal symmetry. Means if you reverse time, the equations retain the same form. Let us see that. Let us look into the first equation first. Right, you see electric field does not change change sign, right? Electric field retains the sign, but this operator is space operator. So I mean there is no point of time here. So the left hand side retains the signature. It is still positive because E is positive under time reversal. Del has nothing to do with time, and this rho is a scalar. It's a charge density. It's a scalar. It does not change. It does not become negative by time reversal. A negative charge will not become positive if you reverse time, or a positive charge will not become negative if you reverse time. It is scalar. It is independent of this transformation. So therefore this equation, the first equation, retains the form. It remains the same equation under time reversal. Now what about the second equation, right? Let us see. See, E changes sign, no, does not. Del changes sign, no, does not. So this left hand side does not change sign. Fine. B will change sign. Fine, because P will go to minus B. So B will change sign. B changes sign. Fine. But T also changes sign. The sign flipping in B and flipping in T will result in that there is no flip. Because B changes sign, t also changes sign, that signature will cancel. Minus here, that minus sign will cancel. So therefore, this equation will still remain the same even if you reverse the time. So the second equation is also symmetric under time reversal. If you reverse time, there is no effect on the second equation. Similarly, if you look at the third equation, look at this equation. This is, so this is nothing to do with time. This will change the signature, become minus. But anyway, it's equal to 0. So changing the signature here makes no sense, because on this side it's anyway equal to 0. So you can take negative common and still it remains the same form. Mathematically, it still is del dot b equal to 0. So it's also symmetric under time reversal. Now this needs to be seen properly. B flips sign, so this becomes negative. This left hand side will become negative because B flips sign. Del will not flip sign, so because del does not depend on time. B flips sign, so this becomes minus. This term becomes minus. J flips sign, so this term becomes minus. Fine. What about this term? E does not flip sign, but T flips sign, so this term becomes minus. The minus will cancel throughout, so it will retain the same form. Beautiful. It's wonderful to see that all the Maxwell's equations, all the 4 equations are time reversal symmetric, which means that if you reverse time, the equations retain the same form. If equations retain the same form under any operation, we say that the laws are symmetric under that operation. So here we are depicting electromagnetic laws, and they seem to be through these 4 equations which we have written, all the laws in the form of differential equations. These equations are symmetric under time reversal. So if you flip the sign of time, then the equations retain the same form. So further, you can also see that under parity operation would mean if you flip the coordinates, you take x goes to minus x, y goes to minus y, and z goes to minus z, or you use kind of a reflection operator. It's called parity. Parity means you change the sign of the coordinates, right? So then what happens? You will see that when you reflect the coordinates, only those vectors which are polar vectors like electric field, current density, their sign will flip. But axial vectors, magnetic field, will not flip its sign. The overall effect will be that all these equations will again remain, they have retained the same form. So we say that Maxwell's equations are symmetric under parity operation. So parity would mean flipping the signs of the coordinates, right? Parity operation would mean, I'll just write it down, parity operation means x goes to minus x, y goes to minus y, and z goes to minus z. This is parity operation. So when you perform this operation, remember, E is an axial vector, E is a polar vector. It's a polar vector. It's a true vector kind of thing. It will flip in sign under parity. And B will not flip its sign. B will remain the same under parity, because B is an axial vector. It's a vector obtained by cross product. And any vector that's obtained by cross product is called axial vector. And that vector does not flip because it's product of 2 vectors. A true vector flips its sign under reflection, but an axial vector does not. So if you put this operation in place, so let's look at the first equation. This will change sign, but this will also change sign. The total effect is that no change in sign. So this equation is symmetric under parity operation. Similarly, you can prove other equations are symmetric under parity operation. You can just look at them and you will figure it out. Let's look at the second equation. Come on. Let's look at the second equation. This changes sign, this changes sign, so no change, because both sign changes will cancel each other. Now this will not change sign, right? Because B does not change sign under parity operation. And therefore the minus sign will remain there. So the form of this law will remain the same when you reflect the coordinates. Same thing happens for the other 2 equations. So we say that Maxwell's equations are symmetric under time reversal, they are symmetric under parity operation, and they are also symmetric if you flip the sign of the charges. That's called a charge conjugation. So you can just have a look and try to understand that how these equations are symmetric under charge conjugation. By that I mean just reverse the sign of the charges and currents. So you will see you have to reverse the sign of charges. Fine. So now, what are the other symmetries, other symmetries of these equations? And the other symmetries are more profound, more important. For example, all these equations are Laurent symmetric. And we'll talk about Laurent symmetry in relativity, and then we'll come back to these equations and we'll show you that how they are Laurent's invariant. There is another fundamental symmetry associated with them that's called a gauge symmetry. The form of this equation does not change if we do some gauge transformation to the potentials. We'll talk about that when we will discuss a full course in electrodynamics. But right now you have to just understand that what kind of symmetries these equations have. They have time reversal symmetry, they have parity symmetry, they have charge conjugation symmetry, they're Laurent symmetric, and then they also have the gauge symmetry. They also have conformal symmetry. We'll talk about this gauge symmetry, conformal symmetry in detail, but that needs a little bit of background. We need to put these equations, we need to redo these equations in the potential form. Good, we'll leave that discussion for a while. So now what we'll try to do is that we'll try to make these equations more symmetric, more beautiful, by supposing that there are magnetic monopoles. Suppose there are magnetic monopoles. How would you write these two for equations? Suppose, does physics permit us? Yes, physics permits that magnetic monopoles should exist, because then the laws of electromagnetism become more symmetric. They become more beautiful, actually. And so let's get into that. So let us write down Maxwell's equations. And when we have these, suppose magnetic monopoles now exist, right? Assume that we have magnetic monopoles, and magnetic monopoles are defined by magnetic charge density. So we have electric charge density we define as rho E, and we define magnetic charge density as rho M. Now we have source of magnetic fields, right, which is like a source charge. We have isolated magnetic charges that can create magnetic fields, and therefore we also have electric current density, like the flow of the electric charges. We'll also have a magnetic current density, flow of magnetic charges, right? This assumption you have to keep in mind. Let us rewrite our equations, Maxwell's equations. So what is our first equation? It is divergence of electric field is rho electric by epsilon naught, because now I will make distinction between the electric charge density and magnetic charge density. And now you first write down this second equation. You just write down this one. What would be the divergence of magnetic field? The divergence of magnetic field would be the mu naught, the magnetic permeability constant, and rho magnetic. So it will be symmetric to our this, right? We have divergence of electric field related to electric charge density. The divergence of the magnetic field will be related to magnetic charge density, right? In the right units, and you'll have to multiply it with mu naught, right? So this is our equation for the divergence of electric field. This will be our equation for the divergence of the magnetic field. What about the curl of electric field? It should look like the fourth equation now. Curl of electric field, it would be minus the first term is there, which was already there, but there will also be a contribution due to current density, right? Because this current density would be magnetic current density. So it just looks like the fourth equation. And let's write down the fourth equation so that we understand the second equation properly. Del cross B is what? Mu naught J electric plus mu naught epsilon naught del E by del T. All right. So now you can see that the physics looks better actually, and it looks the physics of electromagnetism looks nicer actually, right? Now the equations look more symmetric, right? We have two terms. We had only one term here. We had only one term in curl. Now there are two terms. One term accounting for the uh, magnetic current giving rise to electric field, and other term is the change in magnetic field giving rise to electric field. And similarly, we already had these two sources of magnetic field, like electric current generating magnetic field and change in electric field generating magnetic field. So the things look more symmetric. So remember that Maxwell's equations do not deny the existence of the magnetic monopoles. Actually, they demand magnetic monopoles should exist. So there are many people who were looking for the existence, these monopoles should exist, but these experiments always gave negative results. And what about Lorentz force? What will happen to Lorentz force if magnetic monopoles exist? It will have some two terms. So magnetic force on a charge, it's called a Lorentz force. You've done it in high school, is charge E plus V cross B. This is for electric charge in electromagnetic field. Now you have a magnetic charge also. It can also experience electric field and magnetic force. So therefore, we'll say that G would be like magnetic charge, right, into B minus V cross E divided by mu naught epsilon naught. These are actually, these mu naught epsilon naught, they make the everything in proper units, right? So I mean, you need to see that dimensionality, it makes sense. Fine. So now you can see that, you see, we will have a magnetic charge that will experience a Lorentz force of this kind, where electric field has been replaced by magnetic field, and magnetic field has been replaced by electric field. This is kind of electromagnetic duality, right? So I mean, the Lorentz force will have two terms in it. One is then this one that you know from high school, that Q E plus V cross B. But if there is a magnetic charge, isolated magnet, this is an isolated electric charge, which experience force due to electric and magnetic field given by this force rule called Lorentz force rule, there will be a magnetic charge G. If suppose a magnetic monopole exists that has a magnetic charge G, because of a magnetic monopole, if you placed in electromagnetic field, it will experience Lorentz force of this kind, G into B minus V cross B divided by mu naught epsilon naught. It's like magnetic field V cross E, the force due to electric field, and this one is simply a constant that scales it in the proper units, right? So what is the takeaway? Takeaway is that magnetic monopoles, if they exist, the equations of electrodynamics would appear more symmetric, right? It means Maxwell's equations appear to be more appealing if the monopoles exist, but they are not there. They're not there. We don't know why they are not there, but they are not in nature. We don't find them experimentally, and hence we write our earlier four equations. And now we get into something called free space. Let's get into somewhere where there are no charges and there are no currents, right? We get into free space and see how the equations behave in vacuum. So we now take an pure vacuum, and suppose charges are somewhere, currents are somewhere, they create electric fields and magnetic fields. Now these electromagnetic fields are in some vacuum, and we see the behavior of the Maxwell's equations. We'll try to understand the behavior of the fields through Maxwell's equations in vacuum. So let's write down these equations in vacuum now. So in vacuum, in free space, so our del dot E, the first equation, would be 0, because there are no charge densities there. There is no charge in vacuum, right? And then our curl of electric field would retain its value, because it's a equation purely in terms of fields. There are no source terms. It is that del cross E is minus del B by del T. Then we have the divergence of the magnetic field will be 0. Anyway, that is anyway 0, because there are no magnetic monopoles. And then del cross B, since there are no currents, the first term is 0. So the second term will remain, which is the current density term, which is the displacement current term. That term is called displacement current, right? So these will be our set of equations in vacuum. There are no charges there. There are no currents there. There's no sources of electric and magnetic fields in vacuum. But you will say there are no sources, then there should be no fields. But field sources are somewhere. I mean, there could be some currents and charges somewhere, they create fields, but these fields can extend to infinity. They can also go to vacuum. What is the problem? If you have a charge somewhere, some test charge, so some source charge, for example, it creates an electric field. That electric field goes up to infinity. Similarly, changing magnetic field creates changing electric field, and those fields which are changing in time, they can go up to infinity. We cannot stop them anywhere. Our boundary lies at infinity. So when we create these electric fields and magnetic fields, now we are interested in a region where they are not there, that is devoid of any sources. And we'll see that what is the behavior of, how do these equations behave, right? Now what I do is that I take this, my second equation, and that's my fourth one. I take the second equation and take curl on both sides. Let us take curl on the second equation on both sides. So what do we have? We have curl of E. That's equal to minus del by del T of curl of B. Right? Remember here, this operator del by del T and this del operator, they commute. You can, you know, in partial differentiation, del 2x del y is equal to del 2 del y del x. So the partial derivatives commute. So I just write that, this commutes with this, so that's why I've taken it inside. Right? So that's fine. Now I operate this, I use the triple cross product rule and write down what is this del cross E equal to. It is equal to the gradient of divergence of E minus del square E equal to minus del by del T of del cross B is in the fourth equation, mu naught epsilon naught del E by del T. So what I have done is that I've used this equation, fourth equation, and I've substituted it here, right? Del cross E, the value of this del cross E is substituted here. That's why I'm writing this way. I hope it clarifies the idea. Now, del dot E is 0. This one is 0 because that is given in the first equation. You can see that del cross E is 0, del dot E is 0, so this is 0. So I use this, so this is 0, so this is gone. So only this is left and this one is left. So now I write down, what do I get? I write down minus del square E is equal to minus mu naught epsilon naught, I take out, del 2E by del T square. This minus and this minus will cancel. So del 2E equal to mu naught epsilon naught del 2E by del T square. And this is, if you write it in one dimension. If I write this equation in one dimension, if I write it in one dimension, what do I get? I get del 2Ex in first component, del x square equal to mu naught epsilon naught del 2Ex by del T square. And do you remember what kind of equation is this? High school days, you remember this. This is the equation of a wave. It's a wave equation, a one-dimensional wave equation. And traveling with speed 1 by v square. This is 1 by v square. So it turns out that this constant, mu naught epsilon naught, these are the properties of vacuum. Mu naught and epsilon naught, both are the properties of vacuum. And when you multiply them, they're exactly equal to 1 by square of the velocity of light. And it means that the velocity of light, which we calculate in vacuum, turns out to be the square root of the electro and magnetic property of the vacuum. And we can rewrite this equation now in terms of C as del 2Ex by del x square equal to 1 by C square del 2Ex by del T square. So this is the equation of wave traveling with velocity of light. So the electric field, a kind of wave is generated by changing electric field, changing magnetic field generates a kind of wave, and that wave travels with the speed of light. What about this is electric field, and I'm talking only one component. The full wave equation is for electric is del 2E. I will write it here. del 2E is equal to minus, sorry, 1 by c square del 2E by del t square. That is the full three-dimensional wave equation for electric field. So I get a wave equation for electric field. So electric field is like oscillating like a wave. Right? What about magnetic field? I can take this equation and take curl on both sides. From the fourth equation, if I take fourth equation and take curl on both sides, I have fourth equation del cross B is equal to mu naught epsilon naught del E by del T. Now I take curl on both sides. Curl of B is equal to mu naught epsilon naught del by del T of curl of E. All right. And now again I expand this. So it is del gradient of divergence of B minus del square B is equal to mu naught epsilon naught del by del T of, and this is minus del B by del T when you use that equation. Which equation? For del cross E, use the Faraday's law, that is minus del B by del T. Now you know this is 0, del dot B is 0, so minus and minus will cancel. So it is del square B is equal to mu naught epsilon naught del 2B by del T square. So you have a field equation for magnetic field also. So we have a field equation for electric field. We also have a field equation for magnetic field, and it also travels with the speed of the light, that is c. So that means we in vacuum an electric field can generate a magnetic field, can generate an electric field. This way an electromagnetic disturbance will be created which travels at the speed of light. The problem with these equations is that they predict the speed of the wave independent of any reference. And this is for the first time that equations of the physics predict speed. Otherwise, in all equations, we predict speed with reference. We always have speed which is a relative. Speed doesn't have an absolute measure. You need to tell with respect to what. Otherwise, it's meaningless. So suppose I am moving with speed of 100 meters per second, but with respect to what? You have to tell me that whether I am moving with respect to ground or with respect to some other body, and that one has to fix the frame. So for example, you are driving a car, maybe 100 kilometer an hour. But with respect to car, if which you are driving, you are at rest. So unless you don't fix the frame of reference, you can't define speed, because speed does not have an absolute measure. It is always relative to your surroundings. But for the first time, the speed comes in terms of the properties of the vacuum. It comes in terms of the fundamental constants of nature, the electric and magnetic properties of vacuum. It has nothing to do with the reference frame. It has nothing to do with the reference point. So this was quite surprising that there is an equation of physics that predicts speed, and that to a constant speed. It's something like universal speed. It is not dependent on any observer. And this was quite frustrating, that how is it possible that speed is independent of your motion? That means suppose the light beam is traveling opposite to you and you are traveling towards light beam, the light beam still you receive with the same speed. I mean, the speed will not change. So it means that suppose you try to go after the light, right? But say you are traveling towards light at speed c, light is moving away from you with speed c, but still the light will always, with respect to you, have a speed of c only. The relative speed will still be c, it will not be zero, right? And this is total counterintuitive. It doesn't get into our understanding unless we understand that there is something wrong with our notion of space and time. This was the genius of Einstein, which could see that, you see, there is some trouble in the very measure of space and time. And it is the space-time concept that we need to shift our ideas. Then only then we can understand why the speed of the light is not relative, and it gives rise to many other important features. In fact, the speed of light is constant. It becomes the fundamental axiom of a new theory, which we call as special relativity. And we'll be digging into that beautiful relativistic concepts once we finish our this course, this short lecture course on electromagnetism. So this was today's lecture, and today's lecture we focused on the four Maxwell's equations. We talked about the symmetry of these equations, and then we said that if the monopoles exist, then actually the electromagnetism would look prettier, right? The equations will look more elegant. The electric and magnetic fields will look more symmetric, but the monopoles are not there. They're not there. That's it. We can't do anything about it. And then we went into the how do these electromagnetic fields behave if there are no charges and no currents. I mean, we are in pure vacuum, and we have created these electromagnetic fields by charge and current somewhere. Now, do they have the independent existence or not? And we could prove that we have the wave equations. The electric field is a wave equation. Magnetic field also, it waves, it oscillates. Electric field oscillates, and these oscillations travel in vacuum with the speed of light. And guess what? The optics is now, the entire optical spectrum can be understood. The optical phenomena can be understood through Maxwell's equations. And so not only it unified electricity and magnetism, it also entertained optics. It also put optics in its own umbrella, and optics became also the study of electromagnetic fields and Maxwellian equations. And so this was all about today's lecture. I hope that you enjoyed the lecture the way I enjoyed delivering them. So if you have any questions, anything that you don't understand, or you feel that I made any mistake during the lecture, please write down in comments. I will be very happy to answer your questions through the comments that you will have. And in our next lecture, we'll talk about the conservation of energy and momentum of electromagnetic waves, and that would finish our module 1. Then we'll move to the next module, which is the special theory of relativity. And I thank you and goodbye and wish you all the best.